So in this video, I want to show how Archimedes computed the area of a circle and kind of how he thought about the area of a circle. I've got my markers. Okay, so what he does is the following. So notice I have a purple circle on the outside and an inscribed polygon. I'll get to the inscribed polygon in a moment. Let's say this is the center of the circle. And let's say this is the radius of the circle. What Archimedes proves is that the area of a circle is equal to the area of a right triangle whose base leg is equal to the radius of the circle and whose height is equal to the circumference of the circle. Now just doing sort of a sanity check, this is 2 pi r. 2 pi r times r gives us 2 pi r squared, and we divide by 2, that gives pi r squared. And so, interesting. So that gives us the area of the circle. So this is consistent with what we know to be true. So maybe you're wondering why he formulated it this way. The reason he formulated it this way is because if you take if you take an insided regular polygon, then the area of that polygon is going to be equal to the following. So if you look at the distance from the center, not to one of the edges, but to the midpoint of one of the line segments, like this is called the apothem. I'm going to call it A sub n for the apothem for an insided regular polygon. And the area of that polygon is going to be equal to the area with the apothem here and the perimeter of the polygon, which I'm going to abbreviate as P sub n. Okay, so essentially the thing here then is that the area of the circle is just kind of equal to the similar thing with the area of the polygons. Okay, circumference is perimeter. Okay, so here's how he proved this. The first step is to show that by taking n large enough, that is looking at an inscribed polygon with enough sides, that this leftover area is going to go to 0. So in other words, the areas of the inscribed polygons approaches the area of the circle. Now this is a fact that he didn't prove. This is a fact that was in Euclid. It was probably known before. But I'm going to show you why it's true. Okay, here's why it's true. So what we're going to do, I'm going to look at this right here as a representative sample, and obviously this is just an octagon. I think 1, 2. My colleague Catherine drew it for me. So 1, 2. Yeah, it's an octagon, but it's representative of all polygons. And so let me just look at this part right here. I'm going to fill this circle in a little bit better because it's kind of hard to see. And what I'm going to do is the following. I'm going to put this little thing here inside a rectangle whose height is going to be this distance here, and whose base is going to be the side length. Okay, so the area of this little leftover piece here, I'm going to call it L for leftover piece. Okay, I don't know what it is exactly, but I know it's going to be less than or equal to this rectangle that surrounds it. Okay, and I know the area of this rectangle is going to be equal to the side length, I'm going to call that S, times the height. Now, this height, the distance from that midpoint to the circle, is just going to be equal to R minus the apothem. So it's just this distance there. Okay, now what is the side length? Okay, so let's think about this. The side length is equal to the perimeter of the shape. So that is the perimeter of the insided regular polygon divided by n. Because they all have the same size. And then times r minus an. Now, what do I know about Pn? Well, it has to be less than the circumference of the circle. It has to be less than c. because the distance from here to here, the distance from this point to this point is going to be exactly the value of this straight line here, because the distance between 2 points is a straight line, or the shortest distance between 2 points is a straight line. This curve is not a straight line, at least in the whiteboard here. And so what that tells us is that the distance of this curve is greater than that distance. In other words, the perimeter of the circle, or the circumference of the circle, is greater than the circumference of any inscribed polygon. So this is less than C over N times R minus AN. So the area of this green rectangle is less than that number there. Okay, so then the total leftover area, which I will just call L sub T, well, there are N of these. So it's going to be less than, if you total up all of these leftovers, it's going to be less than N times this, which is C times R minus AN. Now as N goes to infinity, AN goes to R. Okay, so if we think about like what would happen if we were to look at a 16-gon, the sides would be something like this. And now the apothem goes from there to there, and it's closer. And so this should be something that is kind of clear from the drawing. As N goes to infinity, AN goes to R, and so this goes to 0 as N goes to infinity. And so what this means is that since the area of the left, so what we're doing is a covering argument. The leftover area is covered by these rectangles, and the total area of those rectangles is going to be less than this quantity right here, and this quantity goes to 0 as N goes to infinity. So what this tells us is that for any epsilon, we can find some N such that the difference between the area of the circle and the area of the inscribed polygon for that value of N is less than epsilon. Okay, so this is going to be important. So in other words, we already kind of know that the area of the inscribed polygons exhausts the area of the circle. That sort of intuitively is obvious just from the diagrams, and then this is sort of a more rigorous proof here. It's not important, but I just want to mention that we actually know that AN is equal to R times cosine of pi over N. And so using some calculus stuff, you can actually show that this is less than or equal to pi squared over N squared. And so if you know that, you kind of have a quantitative bound. You can actually maybe solve. This just says we know AN goes to 0, and so we know there's such an N, but if we know that this quantity here, this total quantity here, is less than or equal to the circumference times pi squared over N squared, or that would be 2 times R times pi cubed over N cubed. We know that over N squared, then we can actually, given an epsilon, we can actually solve for N. It's not going to be important to anything that we do, but I just wanted to point that out. And if you want to know why that's true, ask about that in the discussion, or try to figure it out, but use the mean value theorem. Anyway, okay, forget about that part. So it was known from Euclid's time that the areas of the polygons exhaust the area of the circles. What we need to show now is that these kind of measurements about the polygons converge to the measurements about the circles. Now we know that the area measures converge to the radius, and maybe I'll let you figure out an argument to show that the PNs converge to C, but that's not something that is immediately obvious based on the fact that I talked about when we needed to make sure and be careful with the method of exhaustion. Okay, it's not always the case that the perimeter of the shapes is going to go, it's not always the case that the perimeter of the approximating shapes is going to converge to the perimeter of the thing that it approximates. Okay, so if we wanted to use that fact, we'd have to use something different. We're also, so in essence, what I'm saying here is, in modern language, we might use the fact that AN converges to R and PN converges to C to then show that AN times PN converges to R times C. Okay, but this uses a lot of modern ideas of limits and stuff like that. And those ideas are going to be in the background of what I'm about to show you. But they were not things that were explicitly available to Archimedes. So what we're now going to do is the following. We want to prove this, and I'm going to say that the area, this area, is equal to K. I'm going to call that area K. And I'm going to call the area of the circle capital A. And then the area of these approximating polygons, I'm going to call A sub n. So equals here means the area is equals to that. Okay, so here is what Archimedes does. He says, so what we want to do is we want to prove that A is equal to K. And what he says is, let's do a proof by contradiction. Let's first assume that A minus K is greater than 0. Let's assume that A minus K is greater than 0. Well, given this exhaustion argument with the polygons, what this means is that I can find a polygon such that A minus P is less than A minus K. I can find some polygon such that A minus P is less than A minus K. Because I can make P, maybe I'll even put a sub in here. By taking n large enough, A minus Pn is going to be less than any number, in particular A minus K. If A is bigger, if A is not equal to K, and we're looking at the case where A is bigger than K, then A minus K is positive, and so I can take some n so that A minus Pn is less than that. So rearranging this gives me that K is less than, oh sorry, I need to be, I'm using the wrong notation here. P sub n is the perimeter, but it should be A sub n here. Sorry about that. Okay, so K then, rearranging this gives me K is less than AN. Now on the other hand, AN is equal to 1/2 times the apothem for the nth polygon times its perimeter. Now, the apothem is strictly less than the radius. So AN is strictly less than 1/2. Sorry, AN is strictly less than R. And PN is strictly less, we already talked about this, than the circumference of the circle. But this is just equal to K. So this says AN is strictly less than K. So this says K is less than AN, and this says AN is less than K. Well, that's a contradiction. So what this contradiction says is that A minus K cannot be greater than 0. Okay, the argument that comes next is, what we've proven is that A cannot be greater than 0. In other words, A has to be less than or equal to K. Okay, so now we're going to assume, and I will let you guys do this, we want to assume that A minus K is less than 0. If A minus K is less than 0, you can look at circumscribed polygons and make a symmetric argument here to show, okay, well actually K has, A has to be less than, A cannot be less than K, sorry. And so this contradiction shows A cannot be greater than K. That contradiction that I just described shows that A can't be less than K, so the only option is that A has to be equal to K. I want to do one last thing here. I want to show maybe a way that we can prove this idea prove this fact using the same basic ideas, but maybe stated in a slightly more modern way. And I'm going to do that in the following way. So AN is going to represent all of this stuff, but now what I want to have is I want BN. BN is area of circumscribed. So not the inscribed, but the circumscribed. That is the polygons on the outside. That's the polygon in which the circle is inscribed. Circumscribed. In polygon. Okay, now what we know is the following. We know that A sub n, the area of the inscribed polygons, it's getting bigger and bigger and bigger. Okay, as n goes to infinity, AN is increasing. Okay, and again, if we just look at what's happening here, the area of this polygon is contained in the area of this polygon that I started with the green dashed lines. So the area is increasing. It's also bounded above by the area of the circle. So AN is an increasing bounded sequence, and therefore it converges to some limit that I'm going to call L sub A. Okay, now I also know from the argument that I just gave that I know that AN is less than this value K. So I know AN is less than K. And so this tells me that L sub A, if each term in the sequence is less than K, then its limit also has to be less than or equal to that same value. Not necessarily strict inequality, but we know it is less than or equal to that. So the limit of these polygons is less than or equal to K. The limit of the inscribed polygons, the limit of the area of the inscribed polygons is less than or equal to K. Okay, now I also know that Bn, these are the circumscribed polygons. And as n goes to infinity, they're shrinking and getting closer to the circle. So they're decreasing. And their areas are bounded below by the area of the circle. So Bn decreases down to B. Again, it's a decreasing bounded sequence, so it has to have a limit. Let's call that not B, let's call it L sub B to keep things symmetric. Okay, now I know that Bn, and I will let you guys fill in the details here, Bn is greater than K. And so what this tells me is that LB is greater than or equal to K. And so I have this string of inequalities. LA is less than or equal to K, and that's less than or equal to LB. Okay, now I'm going to just explain this next fact and let you guys maybe think through if I'm going a little too fast here. But I know as n goes to infinity, AN is getting closer and closer to the area of the circle because the leftover area goes to 0. And I know that Bn, I didn't prove this, but the leftover area of if you look at the circumscribed polygons, that also goes to 0 as well. So AN goes to the area of the circle, Bn goes to the area of the circle. So in other words, LA and LB have to be equal to each other. So we actually have equality here. But again, LA and LB are both equal to the area of the circle, so this is equal to the area of the circle, which is equal to K. Okay, if that last part was a little too fast, that's okay. Just rewatch the video and think through what I'm saying here. But I'm just using the fact that we have an increasing bounded sequence and a decreasing bounded sequence. And in that case, we know they converge, and then also we know that they have to equal to each other based on the argument I gave in the very beginning of the video. Okay, that's it for the areas of how he computed the area of, or how he proved this fact about the area of the circle.